Hello, and welcome to the fourth module in a series where I work through a number of example problems related to pistons and cylinders. And this one is going to be a complex one. So let's go ahead and get started and see what we have ahead of us. Little note on the title page says, brace yourself for a tough integral. At least in my world, I would call this a pretty tough integral. And this may be might be the toughest integral that you will experience in this class. And so if you can get over this hump, then perhaps you can worry a little bit less about your calculus skills and integration skills, differential equation skills. It's not a promise, but I certainly, this problem would be classified as, I think, a tough, respectable integral to be able to perform. And so we're going to do a piston and cylinder problem in which the gas inside the piston and cylinder undergoes a path-specific process called PV to the N equals constant. And we're only going to do SI units problem. So when you look at this problem, try to think about how is this problem similar to what we did in example set 3, and how is it different than example set 3? How's it similar? How's it different? Okay. Gas is contained in a vertical cylinder fitted with a piston on top, closed on the bottom. Okay. Initial volume of the gas is 0.25 cubic meters, and the initial pressure is 900 kPa. Those are givens. A gas undergoes a quasi-equilibrium process with a path defined by P times V to the 1.3 equals constant. In other words, pressure times volume to the 1.3 power equals constant. And the volume triples. And the familiar questions determine the final pressure of the gas and determine the work done by the gas during the process. Very typical questions. Okay. How is it similar? How is it different? All right, so let's look for key words. Vertical cylinder fitted with a piston. Again, just as a reminder, when you draw your sketch, start with a sketch. You draw the sketch, write down the word closed system somewhere on that sketch. That's going to demonstrate that you understand that the words of this problem communicate a closed system problem instead of an open system problem. Initial volume of the gas is 0.25 cubic meters and 900 kPa pressure. So in other words, P1 and V1 are given. Quasi-equilibrium process. It just comes out and says it. You don't even have to figure out frictionless means quasi-equilibrium. Okay. Now the process path, the pressure, volume, process path, easy for me to say. The pressure, volume, process path is fully defined by PV to the 1.3 equals constant. That defines a curve on the PV diagram. Also just tells you that the volume triples. V2 equals 3V1. Common questions for engineers: determine the final pressure. We'll use the process path for that, and the work done. Since it's a closed system and a quasi-equilibrium process, we will use integral of PdV to determine the work. Okay, now, have you figured out how come this problem is different than the set from 03? It's all in the process path, a little different. Process path says PV to the 1.3 equals constant. Now in set 3, it was PV to the 1 equals constant. In other words, PV equals constant. PV to the 1. Okay, this one, PV to the, let's say, n plus 1 type thing. 1.3, a number a little bigger than 1. All right, well, let's divide both sides by V to the 1.3. P is equal to constant times V to the 1. Divided by V to the 1.3, or in other words, constant times V to the minus 1.3. And then let's substitute in what the constant is. The constant is P1V1 to the 1.3. Of course, it's also equal to P2V2 to the 1.3, but since we know P1 and V1, let's just put in the P1 V1 to the 1.3 is the constant value. Okay, and so what is that? What's the shape of this going to look like? We've got that on the next slide coming up, but recognize here, so let's plan ahead a little bit. We've got this PV diagram. It's necessary so that we can visualize with our eyes and communicate to others, communicate to our instructor, communicate to the grader, if you have a grader, that you understand that the area under the curve is the work for this closed system quasi-equilibrium process. You could just kind of depict it like that. That's going to be good. That's worth something. All right. All right, so now let's look at the details of this process path. PV to the 1.3 equals constant. All right. The shape of this is called a power, I call it a power curve. In other words, it is slightly steeper than the hyperbola for low values of V. It's steeper than the hyperbola for low values of V, and it's flatter than the hyperbola for high values of V. So visually, it a little bit looks like a hyperbola, but it's kind of steeper. Okay, so just recognize that. So this power curve, PV to the n+1, where n is some number greater than 1, is going to be steeper than a hyperbola. All right. Now, so we've got to be able to integrate this process path. Let's go through the details of that. All right. Workout equals V1, integral V1 to V2 of PdV. So let's take this expression, P equals constant times V to the minus 1.3, and put it in our integral for pressure, P. All right. So now I can pull constant out of the integral because it's a constant. And so in the next step, instead of just writing out the word constant, I wrote out P1 V1 to the 1.3. Integral of V to the minus 1.3 dV. I've got to be able to integrate that. We expect you to be able to integrate this expression. And so before we go to the next slide that's got the work, can you do this in your, well, could you write it out? You have the recipe in your mind of how to do that. Let's see. We've got an exponent, V to the exponent dV. I will increase this exponent by 1. I'm going to add 1.0 to this and divide by that. In other words, this number plus 1.0, divide by that. And then I'm going to increase that exponent, and it's going to be V to the minus 0.3. In other words, minus 1.3 plus 1, evaluated from V1 to V2. All right. So I didn't say that very elegantly, so let's look at it on the next slide. All right. So my note is you have to be able to figure this out on your own, maybe with the help of my inelegant description, but you got to be able to get this on your own. All right. So the constant, you can just calculate a number for if you wish, P1 V1 to the 1.3, because you've got P1 and V1 given in this problem. All right. So here we go. So here's the math I was talking about without writing it down. I've pulled it, you pull the constant out of the integral, then you divide the constant by negative 0.3, constant divided by negative 0.3 times V to the negative 0.3, evaluated from V1 to V2. You've got to be able to see how to get to this. You've also got to be able to work through the algebra. Let's pull the minus sign out of the denominator and get it up here in these parentheses. So we've got minus constant over 0.3 times quantity V2 to the minus 0.3 minus V1 to the minus 0.3. And now I'm thinking ahead towards my calculator work. I tend to do better on my calculator with positive exponents than negative exponents. And so I go to my next algebra step by picking up this minus sign. So I will flip the V1 and the V2 term. So you see, if I bring this minus sign over into here, I can flip the V1 into V2. And another step I make is I change V2 to the minus 0.3 into 1 over V2 to the 0.3. And I change V1 to the minus 0.3 over into 1 over V1 to the 0.3, V1 to the 0.3. That's simply me and the way I did my calculator work when I was a student. I do things in Excel now, and so that helps me in my Excel work as well. But I do this in pencil and paper before I hit the calculator or before I start typing a formula mathematical expression in Excel. So I do this with pencil and paper. Okay. You might want to download this static file to study on this if you're having trouble seeing these integration and algebra steps. It is important that you fully understand how to execute this on your own without writing a formula down and not knowing what the formula is all about. Okay, let's do the numerics of this. Let's work on P2 first. What's the final pressure? Well, I'm going to use the process path and simply write down P1 V1 to the 1.3 equals P2 V2 to the 1.3 and solve for P2. So I've got one equation and one unknown. So I've got P2 is equal to P1 times quantity V1 over V2 to the 1.3. V1 over V2 is 1/3 and for this problem. So P2 is 1/3 to the 1.3 power times P1, or in other words, 215.77. Now, in my world, since I have P1 and V1, I go ahead and calculate the constant. I just so you can see here how I did the work. I wrote in the exponent and I did the math. 148.4 is my constant value. Some instructors frown on that, and that's okay. That's okay. They want to keep P1 and V1 to the end. They want to keep it clean, and so that you can do the algebra and cancel some things out. That's okay. There's no problem with that. So it's just a matter of calculator or computation styles. This is just my style. It's not the way to do it. All right. But anyway, this is the way I do it. And so I get P2 is 215.8 kPa. 215.8 kPa is P2, a lower pressure than P1. Okay. Next, determine the work done. All right, now I've gone through the integration, I've gone through the math, and I'm simply repeating what I found on previous slide. Okay, that's just for you to visualize. So I'm going to write, so here, what was my constant? I calculated the constant offline, and here it is. Here's V2, here's V1, here is n minus 1 or 0.3. 1.3 minus 1 is 0.3. So that's what gives me the 0.3. And so here's my number, 210.6 kilojoules. Okay. So I don't want to convince you, say, wasn't that easy? Oh, it was so easy, trivial. Not exactly. That was kind of hard work. It's really hard work when you go through it the first time in your life. It's not so bad when you've been through it 1,000 times. But going through it the first time is tough. Okay. Let's pretend that was a quiz question and you go, whoo, I made it. I made it through the quiz. Well, I want to go through some alternative math details for this style of problem, PV to the n equals constant process where n is greater than 1. So PV to the 1.3 is constant. But I want to generalize it to just n is greater. It turns out that I'm looking ahead one chapter. I'm looking into chapter 3, by the way. We call this type of process a polytropic process. So, and this is going to align with some professors that cover this right now. Okay, PV to the n equals constant is called a polytropic process. And so what I want to do is show you a simplification process rather than having to calculate the constant like I do straight away. So I'm going to work you through this. We're done with the numerics. There's just a little extra credit on my part, and hopefully you'll follow along. So recognize that P1V1 of the n equals P2V of the n. We knew these two numbers. That's why I calculated the constant. We don't know P2, so that's why you can't. You know what that math is, but you don't know what P2 is. All right. Let's do the algebra, or let's do the integral for work out. Work out is the integral of PdV with the path known, constant times v to the minus n dv. Okay, here's constant, v to the minus n dv. I pull the constant out of the integral. That's all I did here. Okay, next step, I do that power, that integration of v to the something dx. All right, or v to the something dv. All right, so I've got constant. I'm going to take 1 minus n, so in other words, minus n plus 1, divide that into the constant in my brackets. Then I've got v to the minus n plus 1, or 1 minus n, evaluated from v1 to v2. Okay, so I'm doing the algebra now. Constant over 1 minus n, v2 to the 1 minus n minus v1 to the 1 minus n. All right, good. So I am, let's see, what am I doing now? Oh, I see. Next step, I'm going to flip v1 and v2 by flipping 1 minus n into n minus 1. So I'm going to bring that minus sign over into this term. See how I did that? Okay, see, be sure you see how to go from this step to this step. See, I flipped 1 minus n into n minus 1. All right. The next important step is putting something in for constant. Now, it's very clever. I'm over here on, related to this term, I'm going to put in P1V to the n. But tagged onto this term, I'm going to put in for constant P2V2 to the n. Do you see how I did that? Okay, so does that, you see, so you, constant is this times v1 to the 1 minus n, okay? And then over here, constant is p2v to the n times v2 to the 1 minus n. Okay, and so then I've got over on my bracket, I've multiplying this whole right bracket term by 1 over quantity n minus 1. All right, so then I can simplify further. Wow, so look at, I've got to do algebra. v1 to the n times v1 to the 1 minus n simply is p1 v1. So see how the v to the n cancels v to the minus n. Okay. p1 v1. Okay. Same here. p2, so v to the n times v to the 1 minus n is just v to the n. So I get the work out is p1 v1 bracket p1 v1 minus p2 v2 close bracket. All of that divided by quantity n minus 1. That is elegant. That is, it is beautiful and elegant. And some professors, they do this. Fabulous approach. Excellent. Better than my brute force constant equals blah, blah, blah. Elegant and better. All right. And now for a quick story to brag about a student. Okay. We were in chapter 2 and we had a problem a lot like this as a homework problem. Okay. And I was going on and on and on about doing this integral, integrating, know how to do the integral. And the student says, hey, I did some shopping for a formula in the book. And in chapter 3, I found a formula that works. It's really a simple formula. It's equation 354. I said, oh, and I wasn't aware of this. I hadn't read the text carefully enough. And he said, it's P2 V2 minus P1 V1 all divided by 1 minus n. Okay. And I said, wow, okay, all right. I don't recommend it, but it might work. Try it. Okay. And I just kind of dismissed the student. But that student was was sharp. He went shopping in the book for a formula. Okay. And he found a formula that applied. He applied correctly. So you kind of back up a little bit in chapter 3, section 315 applies to PV to the n equals constant half. Okay. There's the result. Okay. And so I had to sheepishly go back to the student and say, you're exactly right. However, you can get to the same result if you start with that integral. Okay. And so it turns out that we were both right. Student was correct. And starting from fundamentals is also correct. All right. And so, I do want to tell you the story about that student that's went shopping for a formula in the textbook. He found a formula. He got that homework question fine. Okay. But the other benefit was we had a good opportunity to have a discussion about not just formula shopping, but really understanding how do you get the result of that formula. So that's important. All right. And so let me demonstrate to you that the formula shopping approach, here it is. The formula from chapter 3 in the book for this path works. You get 210.58. You plug and chug through that formula, you get a result. Or you start with fundamentals, you start with the integral, and you do the integral, okay? And numerically, you get exactly the same result. So these two approaches are identical. And so I just want you to, so your approach, it's very personal, right? So both of these are correct, okay? But I do want to encourage you, to really understand how do you go from fundamentals to the formula. Okay, so I wanted to spend a little time on that. If you don't let anybody kid you, I would say that was not an easy problem. So what's our recap for this problem? Start with a sketch. I've said this 4 times in a row. Look for key words. Okay. Practice working through the math. So this is going to help you get better for quizzes and tests. Working through the math in your homework problems is going to help you perform on your quizzes and tests because you're under the gun. You're under the time clock for quizzes and tests. So the more you practice working through the math on homework, the better you're going to do on quizzes and tests. And thus the downfall of simply blindly using formulas out of the book, calculator, throw down a number, and what's my next problem? Okay. All right, you've got my idea. Seeking formulas in the textbook is poor prep for quiz or tests, and derive your own formulas from the fundamentals. Now, one last slide. Were you totally lost on this problem? Do you still not see how to do the integral of this problem? It is important that you have this integration and math skill to get through this. So if you're still lost, if you're totally lost, I want to recommend that you download my video, in my playlist, ME Prep. I have a little module on integration, practice problems related to integration. I want to suggest that you go through and play that. Doesn't take, it's a half an hour. So see if that can help you refresh your memory on your integration skills. If you're still lost with integration after going through this, I want to suggest that you see your undergraduate advisor, your ME undergraduate advisor, set up a time for a discussion. There is help for students who need to improve their integration and math skills at Virginia Tech. There's help at Virginia Tech to do that, but it's not in the ME department. And so it is my hope that your undergraduate advisor could help you get the help you need so that you can perform well in your ME classes. So I hope that helps. Anyway, I hope that this module has helped you feel more comfortable with what I think might be one of the more complex integrations that you have to do in this class. So good luck. practice, and I hope this helps you with your homework as well. And I'll stop the recording and we'll go from there. See you next time for the fifth and final